Professor, you are so funny, ha ha ha.
Hi, Lucy.
Hello. Oh, hi, Professor.
Did you have a good time?
Yes, it was fun.
Was he a nice fellow?
Yes, very nice.
Did you get a sunburn?
I had an umbrella. Did you see the photo I sent you?
Yes, it looks wonderful. Okay, Lucy, see you at work.
Okay, bye-bye.
Oh, good morning, class. Is everybody ready? You know, Lucy, sometimes I worry about her. You know, Lucy, I worry about you. I kind of feel like your father, your daddy, you know, with all those computer guys that you date. I don't trust them. You know, I don't know.
They are nice guys, Professor.
Oh, you say they are. Okay. Okay, I trust you. Okay, class. I hope you're taking notes because this is all going to be very important. We're now moving into the arena where we're going to put the gases into the chamber. And since they have different expansion ratios as we warm them up, they're going to expand differently. Now, what we have to have is exactly 1,000 cubic centimeters inside the tank. Okay? That's important because when we combust them, then we go to measure it and condense it. We're going to find out exactly how much we got when it's all over. Once the gases combine and they turn into water.
Here is the process of the calculation using the expansion ratios in the volumetric equation. First, our rate of expansion of hydrogen and oxygen is different. Hydrogen is 848 to 1, so 0.207244 times 848 equals 175.742912 cubic centimeters of hydrogen, and oxygen is 861 to 1. So 1 cubic centimeter of oxygen is 861 cubic centimeters when expanded to 70 degrees Fahrenheit. Added together, we get 175.742912 plus 861 equals 1036.742912. Our total cubic centimeters are 1036.742912, thus, we have 1036.742912 cubic centimeters at STP of 70 degrees at 14.7 psi, but we need that to be 1000 cubic centimeters. So, we must reduce the temperature to bring this volume down. The ratio is 175.742912 divided by 1036.742912, which equals 0.169514, thus, 16.9514% is hydrogen and the remaining volume is 83.0485% oxygen. We want to keep our pressure at 14.7 psi, so we will use what is called the isobaric process, when the pressure is constant. T2 equals T1 times V2 divided by V1, or 70 times 1000 divided by 1036.742912 equals 67.51914998, which is 67.5 degrees Fahrenheit. We use the volumetric equation to check our values. And then the isobaric check also. V2 equals V1 times T2 divided by T1, which shows substantial accuracy.
Thank you, Lucy. Now you can see, class, how we use the isobaric equation and the volumetric equation to determine when the gases expand in the expansion chamber into the chamber, we have exactly 1,000 cubic centimeters when we started with 1,036 and change. Okay, so when we expand them up, we have to have the right amount, so when we combust them and they turn into water, we're going to determine how much 1,000 cubic centimeters of the right mixtures of hydrogen and oxygen turned into 1 cubic centimeter of water. Now, before we go any further into the combustion reaction, we're going to look a little deeper into the quantum world. Because when we finally solidify hydrogen from a liquid state into a solid crystal, it turns into a hexagonal crystal. It turns into a hexagon. Now we're going to show you that the hexagon has 7 members. They told me to hold for a count. 1, 2, 3, 4, 5. Huh? Hold for a count. Thank you, Mr. Director. And then we place 3 on top. And they tell me hold again. Thank you, Mr. Director. 1, 2, 3, 4, 5. Can't you delay this in the editing, you know? Okay? And then hold. And then we put 3 more on the bottom, you know, so that makes 13. That's 3 on the top, 3 on the bottom, 7 in the middle. That makes a full hexagon of hydrogen. Now we bring up, I give you another picture. This one is oxygen. Oxygen is a square when it's frozen in a crystal. So now you can sort of start to understand why water makes these funny, pretty patterns. Because the hydrogen wants to be a hexagon and the oxygen wants to be a square. And when you got 2 hydrogens in the oxygen, all of a sudden it's a bent molecule and it starts doing all kinds of weird things. That means it's unpredictable because of what they call the mobility of the hydrogen atom. It wants to move around a lot. So when it tries to crystallize, when it gets frozen at 32, it makes these beautiful patterns. And here's another interesting one. This is called boron. Boron has a rhomboid shape. They say it was made by cosmic ray spallation in a supernova. Not sure how they know that, but I'll trust them. Now here's an image of carbon as a diamond. Most interesting hexagon. It's such a hard crystal that it'll cut through anything, any other element. It'll cut right through it. It's the hardest, strongest element in the periodic table. Now Lucy's going to give you a lot of details about why we need to get away from the traditional model of the atom being proton, neutron, and electron. Because atoms really are liquids that were in the center of a star, and the only way they got out of there is that they collided with another star. And the stars broke up, and all of a sudden all those liquids at really high pressures and temperatures kicked out into empty space and they froze. What you're handling are frozen atoms. Nothing's moving inside. They are hard crystals. This is a break from the Niels Bohr atom, and leave it to Brainstein to come up with the idea, but I'm sorry. It's just that when you start looking and doing experiments, as you'll see later on in the thesis, the Niels Bohr atom just doesn't work. We got to have another model. Now when you start looking at things in the way they really are, as hard crystals, you can understand how when atoms collide and they slam together, they break and they turn into other compounds.
Look, Professor, you don't need to hold up a card. I can just appear anywhere. Tee hee hee hee, ha ha ha, oh my, tee hee hee hee, that's funny.
Lucy, you're so funny. I didn't know computer girls were that funny. Hey. Now Lucy's going to give you some details about the layering concept of particles in atoms. Subparticles on top of subparticles on top of subparticles, and how they were all put together under extreme pressure, and how it takes millions and millions of years for them to evaporate.
The natural state of elements is as a liquid inside of a star, or as a plasma in a nebula at millions of degrees. The substances you handle every day are solid because they are cold comparatively. The professor's break from convention is that atoms have subparticles that are always moving. Electrons do not orbit the nucleus, and he suggests we should break away from the view of attractive forces, as in the theory of the strong nuclear attraction of protons, and the theory of the positive charge attracting electrons that have a negative charge. He will show that electrons are real, and there are forces that move them around. and that they are particles with energy, and that energy is mass, always moving in the path of least resistance. The results of this break in convention does not change the observed actions, and the results are much the same, and the models of atomic structure are right in the layering of particles with energy, as with electrons orbiting, except they don't orbit. All the rules still work the same, but our observation needs correction. The parts of atoms, as in protons, neutrons, and electrons, are all the same thing, but they do not move unless they are pushed. They are at extreme densities the closer you come to the nucleus, and they are stable except entropy is natural, and all atoms decay. The time periods are millions to billions of years. A carbon atom is evaporating, or rather decaying, because it is no longer under the pressure of a star, but its compression of subparticles of sizes even much smaller than the quark, are so dense that unlike carbon-14, whose half-life is 5,730 years, carbon-12, the non-radioactive carbon, decays over millions of years.
Thank you, Lucy. Now I'm going to keep coming back to the push theory with examples and gradually break the convention. And I know it's sacrilege, but when you start finding that things just don't work, you got to come up with the solutions. And I think the issue is the confusion has been magnetism, because magnetisms sure look like they pull each other together, when in fact they're being pushed together. And that's where the pull attractive force came from. And it's an illusion, and we'll eventually see how that illusion plays out and why there is no such thing as attractive forces. There's only push forces, and that's what holds everything together.
So, let's look at our two gases, hydrogen and oxygen. We have evaporated them into the chamber at 67.5 degrees Fahrenheit, and let them sit. The hydrogen in the conventional gravity model is lighter and less dense than the oxygen, so it will settle to the top of our chamber. The electrode is positioned at the line where both gases come together. If it were positioned lower in the oxygen, it will cause no reaction. Likewise, if it were positioned up in the hydrogen area, there would be no reaction. The spontaneous ignition point of hydrogen is 700 degrees Fahrenheit. It seems hard to believe, but true. We could raise our chamber all the way up to near 700 degrees Fahrenheit and nothing would happen. With spontaneous ignition, the pressure is sufficient to break the atoms. And yes, I said break. Now, the hydrogen has formed molecules 2 by 2, and likewise the oxygen is O2. Now, rather than seeing them as a nucleus with electrons singing around in orbits, let's see them as layers of subparticles packed together. They are like hard quartz or silica. Oxygen combines with almost any of the other elements, and we will see that its square crystal is hard and sharp like a diamond, and its mass can break into other atoms. They are held together by pressure. They are no different than balloons, in that if I lower the pressure they expand, and if I increase the pressure they compress. The only difference is that they are so small, that not even air can get between them, because they are the air. There is space between the subparticles, which is why they can compress, but there is nothing small enough to get in between them except perhaps the electron, or the proton, or the neutron. Well, I suppose there are lots of things that can get into the space between them, but they themselves are against each other edge to edge. I can wiggle them with light waves and sound waves, but the only thing that happens when I add energy as heat is they swell. Now, this is no different than the ring and ball that your science teacher showed you in science class. The ball will not fit through the ring, but if I heat up the ring with a flame for a short while, the ring will easily slip over the ball. The ring and ball are made out of brass, and are hard metal. So, it is no different for hydrogen and oxygen. They are hard structures that expand when they get hot, and contract when they get cool. The standard view is that the electrons in their orbits become energized, and their orbits get larger, but that would need an attractive force magically attracting the electrons. It will take time to understand the amazing discovery of dark matter. But, when you begin to see that matter is infinitely small, it all starts to make sense. So, be patient, there is so much more to come.
Thank you, Lucy. What would I do without you? Now we're going to give a breakdown. Lucy's going to give you a breakdown on layering. If you look at the universe and you look at the stars and you look at the planet Earth, everything's in layers.
Layering is a natural function. As Professor Brainstein describes, years ago, his daughter's 6th grade class homework was to do a sedimentation experiment. As it should be, homework for your children becomes a project for the parent, so he set out to find stuff to mix all together as glue, shake it up and then watch it settle for a day or so. Of course, the layers formed, and she got an A for her homework. The byline here is that everything has layers, and the closest example is the Earth. The Earth's layers become more fluid the deeper you go, till you reach the molten core of iron in the center. The Sun is layered, and the planets all have layers that vary in density and activity. So, it should not be difficult to see the quantum world as layered.
Thank you, Lucy. Now we're going to talk about the spectral absorption lines that come off from a spectrometer as being the real vision that we have, the real observation, the way we can see into an atom and what's going on. Because they all produce spectral lines from the smallest element to the heaviest element, and they get really complex. The spectral lines gives us all the details we'd ever need on what's inside of an atom.
This is the spectrograph of hydrogen. There are 4 lines in the visible light spectrum. One is hard to see in this image. It is to the far left in the deep violet range. The color grading behind the lines is there for reference, but when you look at the light through a spectrometer, only the lines show. This is the spectrograph of oxygen. On close inspection you can count 52 lines produced by oxygen, many of which are in the blue and violet range, but at issue here is the possibility of some of the lines being interference patterns. The bands produced are all coherent. That means each band is completely only one frequency. This can cause interference patterns. What is not seen are the bands in the ultraviolet range and higher. There may not be a top end on band count as we delve more into dark matter.
Wow, isn't that interesting how hydrogen has only 4 spectral lines and oxygen has got almost 48 to 58, but then there might be interference groups or lines crossing over lines, because when you get to the core of oxygen it gets really complicated because it's got a lot of protons and neutrons from the conventional model. But what we're going to find out is just layers of subparticles and they're extremely high compression and crystallization. Okay, Lucy's going to give you a lot of good information on the spectral analysis that really shows us the inside of the atom. And how the Niels Bohr atom is wrong, and as we go along in the treatise, you're going to see if this really plays out that the core of the atom is not protons, neutrons with electrons spinning around, because nothing's moving inside of the atom. So we're going to see this, and we're going to see how the spectrum analysis really gives us a lot of insight into the atom and what's really going on inside. Take it away, Lucy.
So, let's look at a coordination of the spectral lines as it might relate to the layers inside a transparent atom of hydrogen and oxygen. The radius of hydrogen is 31 picometers. It is relevant when you look at classical descriptions of atoms, with the nucleus and the electron being separated by a great distance as the spectral lines might indicate. The classical description is, the proton is positive, and the electron is negative, and the electron orbits around the proton. If you add energy such as heat, the orbit expands. The space between the electron and proton is empty. Looking at a green laser through a handheld spectroscope produces a prominent line at 525 nanometers. Of notice for later is that it produces a clean single line coming off of the diffraction grating. In this graphic, oxygen is broken down by the wavelength, measuring 66 picometers in radius. The smallest wavelength produced is 407 nanometers. The longest wavelength produced is 655 nanometers. This is a completely unconventional way of analyzing atoms, but as the professor continues in the treatise, it will gain more relevance. This next slide shows oxygen from its core to its outer edge, and it displays the correlation of wavelength in nanometers to the physical structure of the oxygen atom in picometers. This next enlargement, which shows the scale of nanometers, in between each ring, which is a layer of subparticles, and the thickness of each layer respectively. It is astonishing as to the correlation to the theorized radius of the oxygen atom, and how perfectly it matches the spectrum in tests. This enlargement shows internal groups where there are strong and weak emissions, which could mean internal harmonic resonance. More research will tell. This break with the convention of what is called the Niels Bohr atom is going to be difficult. It is going to be considered radical because so much science has been developed around the standard model. All of that science will still work, only the observation is anew. Some physicists will have a difficult time with this new approach, because they have built so much around electrons orbiting around protons, but now hear this, nothing is moving inside an atom. Yes, electron mass can be added and subtracted causing positive and negative ions. This is how diodes can be made that conduct electricity only in one direction. In one direction the semiconductor conducts freely because it has holes to be filled. Reverse the current and the holes fill up and will not accept electrons to move in. Essentially, atoms are hard, and nothing moves until you add energy and force them to move. Electrically conductive elements allow electrons to come and go. The core of the elemental atom is unaffected. So, here is oxygen. It is layers of subparticles packed together in a hard crystal that can expand and contract just like the ball and ring. Heat it up and it swells, cool it down and it contracts, and it can break like glass when another atom hits it just right, and they combine. The outer layers are more fragile while the inner layers are progressively harder. Just like glass, electrons can stick to it, but it is not actually sticking. The electrons are pushed into the surface and can be scraped off. This is another approach to ionization. Professor, I have TJ Jin on the phone. He said he was listening in and had a comment.
Hi, Professor. How are you?
Good, how are you?
You know, science is so authoritative about things that they don't understand.
I know.
And if they don't have an answer, they just make something
Yeah,
up.
they do.
I'm talking about the nuclear force. Just like gravity, we can't prove gravity waves, but we're sure they're there.
I know.
Like we're sure how atoms are held together. It's the strong nuclear force, right?
Yeah, that's it.
I know, positive and negative, got to be magnetism. The proton is positive, the electron's negative, and proton's pulling the electron. I'm being sarcastic. I just don't like it when science is so authoritative about theories for lack of a better
Yeah,
answer.
the magic magnet force.
You know, that depiction you have of the atoms sure looks like the classic model. The spacing of the proton to the electron, not necessarily electrons. Layers of subparticles.
Yeah, crystals.
Crystallized. Be sure to have Lucy show how that correlation between the wavelength in nanometers to the size of the atoms and the proton and the electron distances in picometers.
Yeah, I'll do that.
You know, if science is wrong about magnetism and the nuclear force, perhaps they're wrong on more than one level. The standard model has just run its course.
It sure has.
And the results are lacking. Well, I put in my 2 cents. Good talking with you, Professor. Talk to you soon. Take care of Lucy.
Talk to you soon.
He's such a nice man, Professor. You should invite him to the laboratory someday.
Yeah, Lucy, I'm going to do that. He is a nice guy. I'll have him come into the lab. We can stand side by side. You know, they say I kind of look like him, but I think TJ's better looking, you know. Okay, like TJ said there on the phone, we're going to show you how the wavelength coming off of the spectral analysis applies to the actual picometer dimensions of the atom. Take it away, Lucy.
Here is the spectrogram of hydrogen. To explain how this works, you find the range of spectral lines and then set a scale in picometers to fit the range. Divide the range in picometers by the range of spectral lines in nanometers. This gives you a ratio. Measure between the lines and multiply by the ratio to see how many picometers the layer of particles consists of. Yes, hydrogen has 1 electron around a proton in the conventional model. If science is wrong about the nuclear force and magnetism, perhaps they are wrong on more than one level. The professor says, he is not a rebel without a cause. The standard model has run its course, and the results are lacking. For science to admit a thing like dark matter, which up to now is a theory, then keep an open mind. It all makes sense in the end.
I don't know. You can't hear your own heartbeat. Oh no, anyway, stick it on your neck, Oh well. Okay, class, from the premise that atoms are hard crystals. We can start looking for other reasons why they do what they do, like forming crystals in square and hexagon and rhomboid, and why they act funny when they crystallize, and make all these pretty patterns like in water. Okay, so Lucy's going to show you some interesting interaction between shapes of different crystals, and how when things get pushed together, they go from round to square in the corner. Pretty interesting. Watch this one. Take it away, Lucy.
We see in the universe common and natural shapes. As previously described, the elements take on crystal forms, hex and square and rhomboid. We see the round planets and the elliptical and discus shapes of galaxies. And if you have seen the water drop slow motion video, you see the droplet pop into a ball. You see children's bubbles wobble in a round shape. Round is a phenomenon which is always evolving but never achieved, as stated in the foreword of the professor's treatise. He tries to avoid saying that the universe is attempting to be more perfectly round, because that implies will or desire. It is not trying to do anything. It, however, cannot stop if it wanted to. Is that not funny? It is not trying to stop, it merely is. Spheres, when pushed together, have forces that push them into a shape other than round. The cones are depicted here to show the way spheres are pushed into a junction point. Here are soap bubbles showing how they join, and depending on each bubble's size and weight, they are pushed into a glob, and I mean glob, not globe, that finds a balance or a sum solution to all the forces pushing on them. In the junctions it is anything but round. 3 spheres alone cannot form a structure. It takes 4 to form a structure that can be fused. Fusion will be discussed later. Notice the black lines that show the center of vector force. The red lines indicate the triangulation planes formed by the spheres. Center of gravity here is a drafting term. It was at this point in the development of this thesis that the professor needed more tools to describe the tank experiment, and the amazing reaction that would take place in the chamber. He knew that there were some critical observations that he needed to make. It sent him into months of experiments to show some critical points about nature and light itself. So, put on your seat belt. In episode 5 comes some really cool stuff.
Yeah, you know, soap bubbles, they show us more about the universe than, you would think. Little old simple soap bubbles. That shows spherical interaction in the junctions and the crystallizations and the way shapes interact with each other. Okay, class, hope you're taking notes. We got a lot of territory to cover. It's a big thesis. Next time, this pretty much wraps up episode 4. Next time in episode 5, we're going to go into the lab and we're going to do some serious experimentation that really shows that propagation velocity is dependent on frequency, which all of physics says, no, that's not true. I'm going to prove that it is. Thanks for joining me. Kids, where's Dixie? Where's Dixie? The neighbor's dog is here. Charlie. Charlie. This is Charlie. Plays with Dixie all the time. It's the neighbor's dog. I think Charlie's deaf. But they say no, but I holler for Charlie and Charlie can't hear nothing. Charlie can't hear nothing. Let's see, can you hear? Can you hear? No, I can't hear nothing. Let's see. Oh boy, you're healthy. Oh, you're healthy, dog. Charlie, hey kids, where's Dixie? Charlie wants to play with him. There you go. There you go. I'm not a doctor, I'm a psychologist, a physicist. That was Charlie.